Hello, everyone. Let's get started. So thank you for joining us today. I'm Sajun Nitikadan, and I'm the marketing manager here at NanoServe. So just a few basics before we get started. As we go along with the presentation, if you have any questions, please send them to the Q&A tab on the lower portion of the screen. Please do not use the chat tab because this is kind of hard to keep track of the questions in the chat tab. And we'll try and answer all your questions towards the end of the session today. In case we do not get to your questions, we'll get in touch with you directly and give you the answers directly. You can also reach out to us at info@nanosurf.com. And this webinar will also be recorded and will be available on our website if you want to watch it later, or if you want to pass the information on to your colleagues. So today's webinar is titled More Than Topography. What else can AFM measure? Our presenter today is Dr. Dalia Yablon. Dalia is a founder of Surface Car, a nanoscale measurement, consulting, and training company in the greater Boston area. So Dalia has over 20 years of experience in nanomechanical characterization methods. She also serves as a technical co-chair of the Nanotech conference, part of the Tech Connect World. She holds an AB in chemistry from Harvard and a PhD in physical chemistry from Columbia University. So with that, let me go ahead and turn things over to Dalia. Dalia?
Thank you, Saju. Is audio okay? Everything's clear?
Yeah, the audio is good.
Great. Okay. Thank you so much for the introduction. Good morning or good afternoon to everyone, depending on where you are. Hope everyone is healthy and well. So the focus of today's webinar is going to be on what it can do in addition to topography. Sometimes there's a bit of a lag in the first advance. There we go. My first slide, I like to focus on showing off a little bit what AFM can do with the 3D topography measurements that it is so famous for. So I've just collected here some images from different applications just to show the power of the AFM topographic measurements. I'm starting off here. This is an image very recently collected of multi-layer graphene oxide, where you can see all the different layer thicknesses here, the thinnest one being just over a nanometer. So very high resolution here. Here I have a couple of images of using AFM to map the topography of biological species, something that it's uniquely capable of doing in terms of imaging these in physiological conditions. So this is an image of a live E. coli cell, and this is an image of a human lung cell. Here are a couple more high resolution images. So this is a 450 nanometer by 450 nanometer image of gold particles. You can see the individual particles. And here's a 500 nanometer by 500 nanometer image of anodic aluminum, also a high resolution image. And then the final image I like to show is a very pretty image of butterfly wings, showing the very unique periodic structure found in these wings. So all of these topographic measurements can be done with very high resolution, so 5 nanometers in X and Y, and less than a nanometer in Z, as well as flexible environments, right? That's part of the power of AFM, is to collect high resolution measurements in environments such as air and fluids. We don't have to go to vacuum, where some of the analog electron microscopy measurements are. And then just one industrial application where these topographic measurements are really key, and that is the semiconductor industry, where they use AFM as a quality control tool for critical device metrology. So they've got these features in their devices, these trenches, for example, here, and they have to very accurately measure the width, the depth, the roughness along the floor, the sidewall, and up here. And the three-dimensional topographic maps that AFM can construct are extremely useful and important. Like I said, AFM is a main control tool for kind of metrology measurements. But AFM is so much more than just a topography mapping measurement. It can measure so many other useful surface properties. And in fact, in my own work, 95% of measurements I do for customers have to go beyond topography and have to measure some of these other very useful properties that AFM can offer. So I like to think of AFM really as an umbrella for many different modes that can probe many different surface properties. And I lump them into the following categories. So we've got mechanical modes to measure different mechanical properties of our material. We've got electrical modes to probe different electrical properties. We even have a magnetic mode. The storage media industry uses this one extensively to look at quality control on their media. Past few years have seen increasing activity in optical modes, where we're now combining some optical signal together with AFM. And so all the modes listed in these categories, this is not even close to an exhaustive list. It's not meant to be an exhaustive list. It's just picking perhaps some of the more common modes out there. And all of these are essentially imaging-based methods. So you're imaging a property of the surface. But AFM is actually capable of doing even non-imaging type of measurements, which I put loosely into this other category. So for example, can do electrochemistry. You can have these molecular pulling measurements where you grab onto a protein, for example, and you pull on it and watch the unfolding events. The AFM tip can be used to manipulate or write structures on the surface or manipulate features, move them around on the surface. So it really is a very powerful tool because all these properties it can measure, all these things it can do, and measures simultaneously with topography, thereby providing a very complete characterization tool with nanoscale resolution. And I'm going to go into some modes in each one of these categories and describe how they work and how they're used. So first, to make sure we're all on the same wavelength with how the AFM operates, here is just a brief schematic for principles of operation. So we start off with the cantilever. It's very small, dimensions of the human hair, about hundreds of microns long, tens of microns wide, and a few microns thick. And hanging off the end of that cantilever is a very sharp tip that's going to interact with our sample. As this cantilever tip assembly interacts with the sample, we have a laser that's reflected off the back end of the cantilever and directed towards a position-sensitive detector. Now, this position-sensitive detector can track motion both vertically, up, down of the cantilever, as well as side to side of the cantilever. And depending on what you're trying to measure, you will take advantage of all of those capabilities. Now, in terms of the scanning, here we have a sample, a schematic for a sample scanning instrument. So the piezo is underneath the sample, which means it moves the sample for whatever scan size you want. And it moves, and then the tip can interact with that sample while you're scanning. And we have so many different ways of interacting that probe with the sample. And through these different interactions is how we can access these different properties. Many of these interactions will require the use of what you see here called the shake piezo. The shake piezo is used to tune the cantilever, to shake it, tune it to a particular frequency. You might want to tune it to an on resonance of the cantilever or off resonance, depending on what kind of measurement you're doing. But again, a lot of variability, a lot of options here for how we interact our probe with our sample. So let's start with examining what the different properties we can measure are. And we're going to start with mechanical properties. Mechanical properties are actually the first properties that AFM was exploring into topography when it was first invented over 30 years ago. And this mechanical contrast image I'm showing here is called phase imaging. It's been around since the early 90s. It's still very popular and common, often used. And what phase imaging does is it provides image contrast based on material properties. So here I have a 5 micron by 10 micron image, topography image of a 5-component blend. It's actually pretty complicated. I've got 3 rubbers, a polymer, and a nanoparticle, silicon nanoparticles in here. You can probably make out the silicon nanoparticles with these little yellow dots here. But in terms of those other 4 components, it's very difficult to distinguish them. So then we can go to the phase image. What the phase image is when we drive the cantilever at resonance, it interacts with the surface, and then there's a phase lag in the response relative to the drive. That phase lag is going to be due to a convolution of material properties, including properties such as stiffness, adhesion, viscoelasticity, and dissipation. But the convolution of all those properties into one gives you contrast based on your material. And so now in the phase image, I can see a lot of different information from the topography image. For example, I can see I've got this one region here that's bright and white. Here I see a domain that's yellow. So definitely got a lot of yellow component here. Then there is this reddish brown here, which you can see, clean areas of reddish brown. And then if we were to zoom in, we could see around these little purple particles, there's actually a dark purple component as well. So thanks to this phase image, I can now distinguish the 5 components very clearly in this material, which I certainly could not do with the topography image alone. And what I do is I can overlay, I can paint the phase image onto the 3-dimensional topography, resulting in this image shown here. Now, this is very useful because it can provide me with a correlation of the material properties with the topography. So I can see if these white areas, if there's any unique or unusual morphology correlated to them. Not so much in this case. But you can obviously see the particles, these little silica particles that are jutting out. They're a very, almost like a blackish contrast. And around them is this purple contrast, which is one of the components. So the phase really gives us a lot more insight into the sample than just the topography alone. So phase is a qualitative imaging mode. Now we could actually do some more quantitative mechanical measurements to look at the stiffness and adhesion of your sample. And so a couple of weeks ago, we did a webinar of focused very heavily on this technique. It's called force spectroscopy, which are these force curves where you take your AFM cantilever and you poke in and out of the sample. And as you poke in and out of the sample, you measure the cantilever deflection as a function of the piezo movement. And when you do that, you see a profile such as the one shown here. So here we approach our surface. Then we're going to snap into contact. Now we're in contact with the sample and we're going to push against it. That's what's called the repulsive wall. As we reach the deflection set point, we then reverse, shown here. We get a little bit stuck in the sample as we pull up, and then we go all the way away. And so the adhesion information is captured in this part of the curve. And the modulus or stiffness information is captured in this part of the curve, depending on what model you use. So this is an example of a single point force curve measurement. You could poke your sample in an array. And so we can create a map of force curves where we create an array of these pokes and we extract the adhesion and elastic modulus, but now we get a map of each property on the surface. So this is an example of epithelial cells. So here's the adhesion on these epithelial cells, and we can quantify it and extract the histogram of the adhesion and see how homogeneous it is on the cell surface, fairly homogeneous here. And we can do the same thing for the elastic modulus, as shown here. And here we've quantified it in our histogram for the cell here. And here it is on the background. Here we can actually see there is some heterogeneity in the elastic modulus on the cell surface. But this is a way of quantifying the mechanical property, which is a little bit different than what we showed with the phase image, which was the qualitative material contrast for the image. Now, the very first mechanical property measurement ever done with AFM was lateral force microscopy, or LFM, to measure friction. What we do in this mode is we scan at an angle perpendicular to the cantilever axis, and we measure the side-to-side motion of the cantilever as we do this. And through calibration, we can then correlate that to the friction on the surface. So here's an example I pulled from literature from Xang published in Carbon in 2017. And this is looking at graphene. So this was topography measurement of graphene, and there are multiple layers here. So some are thicker than others. And then this is the lateral force mode or friction image of corresponding to the topography. So we see that the friction is much lower here than on the silica dioxide substrate surrounding it, not surprisingly. But then they looked at the correlation of the friction with the thickness, showing that the thicker layers of graphene actually had the lowest friction, which is not surprising because graphene is known to be a good solid lubricant. And we know that through these kinds of LFM measurements, because there's no other technique that can measure the friction of a thin layer of something like graphene. Okay, so this rounds out our some of the modes that I want to highlight for mechanical properties. Like I said, there are so many. I could spend probably a whole day just talking all the different modes, but this just highlights some of the more common ones. Some other things one can do with AFM is a measurement like electrochemistry. You can place you can do AFM measurements inside of an electrochemical cell. And therefore you can measure the topography or the morphology as a reaction is occurring. So here's an example of copper deposition on a commercial polished platinum electrode. And so when the potential is a certain value, you can see the copper deposit on the electrode. And then they changed the potential and the copper particle all dissolved, all went away. So you can actively monitor and track these actions as a function of the electrochemistry. This is very popular for corrosion studies. A lot of corrosion work has been done with this. Another kind of measurement that I put into the other category is a measurement called FluidFM. So FluidFM takes advantage of these hollowed out AFM probes like the one shown here. You can see the opening here is a couple hundred nanometers, and it's integrated with a microfluidic system so that fluid can be pumped, pressurized, pumped through, or sucked out of this hole. And one very useful application of this mode is in the biological community to conduct reversible and facile cell immobilization onto the probe. It's actually quite difficult to immobilize a conventional AFM probe. It's very consuming and it's not reversible. So once you get on there, you're stuck. Through FluidFM, it's reversible. It's pretty easy to get it on. And this is great for cell adhesion measurements, those mechanical property measurements that I discussed before, that otherwise are not possible to do. And here's an example of cell adhesion in a yeast cell and a mammalian cell shown here. All right, so now we're going to shift gears and go into a brief overview of some of the more popular electrical modes that AFM operates in. Again, the idea here is to provide our usual topography, but now also channels that provide contrast based on electrical properties. These modes require an electroconductive tip. They're commercially available and only a little bit more expensive than conventional silicon cantilevers. There are many different electrical modes. And again, this is not an exhaustive list, and I'm not going to go through all of them, just some of the more common ones. So I'm going to go through conductive AFM, which measures charge distribution and transport. KPFM, which is Kelvin force microscopy, to measure surface potential. AFM, that is electrostatic force microscopy, to measure long-range electrostatic forces. MFM, magnetic force microscopy, to measure magnetic interactions. And finally end with PFM, piezo response force microscopy, to measure ferroelectric domains. Just a quick note on PFM, reflecting the alphabet soup of modes that is the AFM world. It actually stands for multiple modes. PFM can also stand for a mechanical mode called pulse force microscopy. Now, many of these electrical modes require the ability to image your sample in 2 passes. The first one is to collect the topography of your image, as shown here. Then you lift the camera up a few tens of nanometers at a distance described and optimized by the user. And now you're going to trace out the topography in this lift mode. And while you're going to apply a bias to the probe, an AC or a DC bias, depending on what mode you're trying to measure. So many of these electrical modes will rely on this dual pass method. So the first mode is conductive AFM. You can obtain a localized map of conductivity of your sample with conductive AFM, where a conductive tip is scanned in contact with the surface while a voltage is applied between the tip and sample. This generates an image of the current between the tip and sample. This example shown here shows a topography and current image of a lithium-ion battery cathode, which is a composite with multiple materials. Its different components can be assigned thanks to this mode. In the current image on the right, and here below, actually, the current image has been overlaid onto the topography image in this overlaid image, similar to what I had shown earlier with the phase image. Here in the current image, the less conductive purple regions here, these are the regions in the material that are the lithium cathode material not covered with polymer binder or conductive additive. The more conductive regions here in pink are where the lithium cathode material was covered with a particular binder and conductive additive. So with this AFM, we can get a much better understanding of where the conductive areas are. The next technique is KPFM, or Kelvin probe force microscopy. This maps a variation in conductive potential between the tip and sample, which can be converted to the work function difference between the two. It is also referred to as surface potential or work function imaging. It is often used as a qualitative technique, but be quantitative as well, some additional effort. Applications of KPFM are diverse, and they include studies such as corrosion, photovoltaic effects in solar cells, and catalytic activity. It is another example of mode that gives us sensitivity or contrast on the electrical properties in the sample. In this case, it's work function. Here is an image of a gallium arsenide surface with gallium arsenide oxide interface layer. Here we see the topography image. One more thing. We charges were placed in the surface by the tip through a voltage application. So here on the left is a topography image, and it looks pretty boring, right? It's homogeneous and smooth. There's nothing really to look at. On the right, we see the KPFM image, where you now can see the pattern of buried charges very clearly exposed. The final electrical method I will survey is electrostatic force microscopy, or EFM. This method maps the effect of long-range electrostatic force gradients on an oscillating cantilever and is useful for applications such as electrical failure analysis, measuring charge distribution, and detection of trapped charge. it is a convenient method to image qualitative electrical properties as the electrostatic force is measured between a biased cantilever and the surface as the lever is lifted a prescribed amount in the dual pass mode that I had described previously. This example here is of amorphous bits on a DVD RW, where here we can see the EFM image that clearly exposes these foreign bits not seen in the topography image. The magnetic analog to EFM is to probe magnetic properties through magnetic force microscopy. Just like in EFM, we take advantage of the dual pass mode here, where the cantilever is lifted over the sample and the tip sample magnetic interactions are detected and used to reconstruct the magnetic structure of the sample. So this image here is an MFM phase image of a hard disk drive. Here we have the topography showing the topography tracks, while the MFM image here shows the magnetized domains with magnetization reversal, where white represents repulsive forces and black represents the attractive forces. Now, a good example where we bring in now a couple of these modes to try and get a more complete visualization of the sample is shown here. It's looking at stainless steel. So here's the topography image of stainless steel. We see some polishing scratches, not very exciting. And other than that, we don't really see a whole lot. The MFM image in the middle, though, clearly differentiates now the different domains in the steel surface, revealing these yellow domains here, which are the austenite phase, and this worm-like domain here, which is the ferrite phase. We can then continue and collect a KPFM image, which I discussed earlier, one of the electrical modes, to look at the surface potential difference between the different domains. And here again, we can see very nice contrast between the austenite domains and the rest of the surface. So here you see the MFM and KPFM modes providing a more complete understanding of the surface than obviously just the topography alone. Okay, the final electrical mode is piezo response force microscopy. This image is a piezoelectric effect of the conversion of mechanical deformation to electric charge. In this mode, an AC bias is applied to the tip in order to induce mechanical deformation of the sample that can then be measured by the cantilever's deflection. This is an image of lithium niobate. It's a common piezo material which has domains spaced apart by approximately 10 microns. What we've done here is actually overlaid already the piezo response onto the topography. So the topography alone, you can kind of see between these purple and green domains, there isn't a whole lot of variation. The topography is not able to differentiate these domains. But the out-of-plane piezo response clearly very easily visualizes the different domains in this material. There are certainly other electrical modes available with AFM. This was just meant to be an overview of some of the more common ones. The final category I want to discuss is combining AFM or using it as a platform for optical measurements. Now, optical measurements can provide a really important key of adding chemical information or specificity to AFM topography. And there are two main avenues for this. We can combine AFM with Raman measurements and then AFM with infrared or IR measurements. For AFM and Raman, the most common way to do this is to perform what are called co-localized measurements between AFM and a confocal Raman. So your AFM functions the way it does, and then a confocal Raman focuses its beam on the area underneath the tip to collect the Raman signal from that particular area. Now, there is another technique called TERS, or tip-enhanced Raman spectroscopy, where you actually use the AFM tip as an antenna to focus the light right underneath the tip. This gives you much higher resolution. But TERS is actually very challenging to operate, and there are really only a handful of niche applications that it's useful for. The other technique, which has had a lot of development over the past few years, is combining AFM and IR. So the first technique, which is an apertureless scattering method, is similar to yours, where the IR light is focused underneath. So the tip again functions as an antenna, and the IR light is focused right underneath there. Again, giving you really good resolution. Another approach to combining AFM and IR is to basically zap your laser, the IR laser, it heats it up, and then your sample expands, and against the cantilever rings from you can extract the IR spectrum. Now, being able to combine any of these optical techniques is so useful is the resolution limit of these optical techniques on their own. Any optical technique, its resolution is going to be limited by the diffraction limit, which is the incident wavelength over 2. For a technique like IR, is very long wave, that means your best resolution was on the order of a couple of microns. Not impressive. When you're able to combine it with an AFM technique or run it off of an AFM platform, your resolution becomes impressive. It can be less than 100 nanometers. And then both these techniques, both the Raman and the IR, getting along with the AFM, you're getting along with all the AFM information that can be provided. So not just topography, but also the mechanical property and even electrical property info. So these optical techniques are really providing a very useful additional axis of measurement of this chemical specificity to all the different properties that we've already described. All right, so here's an example of AFM with co-located confocal Raman measurement. This is an example of graphene. A lot of AFM-Raman measurements are geared towards the carbonaceous materials because Raman is exceptional at being able to distinguish and identify materials like single-wall nanotubes, multi-wall nanotubes, graphene, diamond-like carbon. So you'll see a lot of work in the AFM-Raman area on carbonaceous materials. So here's a topography of our graphene flake, and there are different thicknesses there, so different layers. And then what they did is they collected an image focusing on a particular band in the Raman spectrum. So for example, a single layer graphene has an identifying band, as a double layer graphene and 3-layer graphene. And so then they collected the image of just the band for single layer graphene to map out where the single layer graphene was. Same thing for the 2-layer graphene and then the 3-layer graphene. And then you can put it all together into this composite image here, where you can now very nicely visualize on the topography where all your different graphene layers were. Now, here's an example where we can put all the information we've discussed together. So this is still our graphene flake here with the topography, and then the composite Raman image giving us all the chemical information. We can collect a phase image. If you remember, that was one of the early mechanical properties I had talked about. It's not actually a whole lot of differentiation in the phase image here on all these different layers of graphene. But then we can actually look at the contact potential image. So this is the KPFM image, and now we do see differences between these different layers in terms of their contact potential. So putting all this information together really gives you quite a complete characterization and visualization than if we were just stuck with the topography alone. So my final example here is an example of how to use AFM-IR. I am a chemist, so infrared spectroscopy is near and dear to my heart. A very powerful tool for chemists in terms of identifying fingerprint functional groups and molecules. So this here is an image. It's just a regular topography image of a dye block thin film, PMMA and polystyrene. anyone who's done a lot of images on AFM of these dye blocks know that they really result in these beautiful structures on the surface, beautiful patterns. So when we look at this topography image, we can clearly see the two different components, right? One's, I guess, topographically higher than the other. And the question is, which component is which, right? Which is a PMMA and which is a polystyrene? And I don't know from the topography image. I could collect a phase image and I could try and infer that. But again, the phase image is really more of a qualitative contrast. It can be tricky to really identify materials based on just a phase image. So we can rely on an AFM measurement. Now we're collecting the IR off of the AFM, was an apertureless scattering method. And what they did in this image is they sat on a particular band, the 1730 wave number band, which is a carbonyl stretch in PMMA. And they collected an absorption image of where was 1730 wave numbers being absorbed and where was it not. And what they see, so these bright areas here is where it was absorbed, indicating that this is in fact where the PMMA was. And the dark regions was polystyrene, where there was no PMMA peak. So this is incredibly helpful because now we unambiguously know which component is which. And just to make double sure that this is not some kind of artifact, they turned off resonance into a spectral area where there isn't really strong absorption of any component, 1650 wave numbers. And you can see here a very weak contrast between the two components in this dye block. Unlike when you're sitting on one of the peaks, on resonance on one of the peaks, you get very good contrast. So adding these kinds of chemical specificity is really exciting and really enhances our interpretation of these images. Okay, so in conclusion, I hope I've been able to convince you that AFM is so much more than just a topographic tool. We can probe mechanical properties, electrical properties, chemical properties increasingly like Raman and IR, and even magnetic interactions, all with very impressive resolution and flexible environments. So with that, I thank you for your attention and would be happy to take any questions.
Thank you, Dalia, for that interesting presentation. I hope the attendees now have a better understanding of the capabilities of AFM and now investigate if the other modes of AFM is applicable to them and to their work. So we have a few questions in queue already. We'll answer them in the order that they were received. And if you have any questions, please send them to the Q&A tab. And for those of you who might be interested in learning more about the other modes of AFM, we have several demos scheduled in the upcoming weeks. Next week, we have a demo on KPFM using the nanoscale flex axiom. And as Dalia alluded, we had one last week on the force spectroscopy using the flex axiom AFM again. And that demo is recorded and is available on our website. So if you want to watch that. And if you have any other modes that you would like to see, please let us know and we'll try to include them in our schedule. So questions. When you say adhesion on phase image, which adhesion do you mean? Adhesion of a coating, particle, or other?
So it would be whatever adhesion is in your sample. It's actually technically the work of adhesion of your sample. And again, the phase image, what it's doing is it's convoluting a number of properties into the contrast, adhesion being one. But again, it's simply adhesion of whatever your sample is. As a tip is pulling out, it's usually a silicon tip. You could use a coated tip if you're interested in a different interaction, but it's the adhesion of your sample with that silicon tip.
Okay. Can we use AFM for powder samples or just for thin films?
Absolutely. You can use them for powder samples, for thin films, anything that fits into your microscope. I used to, before I started my own company, I was at ExxonMobil. And one of the most interesting parts I ever had to look at was an engine part. And they cut it up and they stuck it in the instrument. We were looking at these at lubrication of the surface, but as long as it fits into your instrument, you can image it.
Okay, this is a mode that you didn't talk much about, but what is thermal microscopy, scanning thermal microscopy?
Sure. So scanning thermal microscopy are measurements where now you can do heating with the tip. So it's a specialized tip that you have to buy, and you can heat directly the localized area right underneath your probe. So it's for localized thermal measurements to look at transitions like melting points or glass transition temperature. But it's the ability to make these localized thermal measurements through these specialized tips.
Okay. Can AFM be used to quantify and qualify the adhesion of glue onto a surface?
So you would have to, you would have to try, I guess, and get a coating of a glue or some semblance of that onto the tip. Remember, what you're measuring in terms of the adhesion, it's the work of adhesion between your silicon tip and your surface. So you could, like I said, try modify your probe with a thin coating of the glue and make measurements onto whatever your surface of choice is, but it just requires tip modification.
Yeah, and also they can go with the colloidal probe.
Yes.
You want to use a bead.
That's true, yes.
Yeah, I think there's a misunderstanding here. It says KPFM can give information on corrosion. Would you mind explaining a bit of detail of what can be obtained in terms of corrosion? I think it was more electrochemistry where you talked about corrosion.
Right. Yeah. So in the electrochemistry, there are purpose-designed electrochemical cells that you can operate the AFM cantilever in, and then follow the reaction, if you will, the electrochemical reaction as it's occurring. With KPFM, I don't know if this is what you meant. You're applying a potential in KPFM. So you can use that also to probe, the potential during the reaction as well. So I'm not sure exactly what that meant, but I'm hoping that covered it.
Okay. Yeah, if this is not a satisfactory answer, please contact us at info@nanosurf.com and we will get back to you. Okay, so the combination of AFM with IR and Raman, can it also provide a chemical signature in addition to topology as IR and Raman when used alone?
Yes, so the answer is absolutely. It depends on what mode you run it in. So the modes that I showed you were imaging modes where they sat on a particular frequency and absorb and set that frequency. So that's conducive to imaging. But you don't have to image. You could sit on individual points and collect a full spectrum, either your Raman spectrum or your IR spectrum at that image. That's obviously pretty slower, collecting a whole image at just absorbance of one frequency, but it's certainly doable. And certainly a very popular application to just sit and collect localized spectra at individual points.
Okay, what are the forces that are involved in adhesion? I think that's the whole thesis project there.
Yeah, so that's like loosely the work of adhesion, but it's actually a pretty complicated question.
Yeah. Okay. Can we detect?
It's kind of beyond. It's beyond the scope of a brief 1 minute answer here.
Exactly. Yeah. What are the forces involved? There are just too many forces. Yeah. Many different things. Can we detect electrostatic interactions in the force curve? Now that's more specific.
Yeah. Sadly, I would say sometimes you can. Sadly, because that's not your intention. Sometimes you will pick them up if you have strong electrostatics between your between your tip and sample. But yes, you can certainly pick those up, especially if you design your experiment in such a way that you're actively looking for them.
Okay. Do you need any kind of special substrate for measuring powders?
No, you would just need a pretty flat surface, mica, silicon wafer, all good, that, you know, could just support the powder.
Okay. Can you perform in situ AFM imaging, liquid AFM imaging with your instruments? I'll take that. Simple answer is yes, we can. Both our core, flex series can image in liquids. When we talk about adhesion, is it adhesion between two layers or between the sample and its substrate?
Okay, so thank you for clarifying that. It's between, it's actually, I don't know what sample and substrate means. It's the adhesion between the cantilever and your sample. So when you measure adhesion, you're poking in at a particular point on your surface. And the adhesion is between your tip, which is typically made of silicon, unless you modify it. So it's adhesion between your silicon tip and the material in your sample.
Okay. Next one is a more specific question. What kind of spectrometer was used to measure in the PMMA-PS? Was IR spectrometer or Michelson?
It's definitely, no, it's a purpose-designed Michelson interferometer. It's not an IR spectrometer. It's a Michelson interferometer in conjunction with a very high-powered mid-IR laser. And again, that technique, that particular one is focused on it. It's a near field technique. I don't know if that means something to the person who asked the question, but it's near field, which means, so the light is reflected off of the very end of the tip, and the tip is very close to the surface, and it's operating in the near field, right? So the tip, as opposed to the far field. But it is a Michelson interferometer based measurement.
Okay, now this is again on the adhesion. So what is the use or application of measuring the adhesion between the tip and the sample surface? Yes.
Right, so there are actually a lot, because silicon is actually pretty inert, so it doesn't really interact with a lot of samples, and it's a really good baseline material. So if you're trying to compare, you know, different surfaces, or, you know, you just said, there's so much literature out there right now already on adhesion measurements on all sorts of materials. It kind of gives you a good baseline. But again, silicon is fairly inert, and that's exactly what you want. So that what you're really trying to understand is the work of adhesion, which is a property of your material.
Okay. I think we've answered most of the questions at this point. If we have missed any, we'll get back to you directly. So once again, Dahlia, thank you for the presentation and addressing all the questions of the attendees. And to all of you who attended, thank you for attending this webinar, and we look forward to seeing you at one of our future webinars.
Thanks, everyone. Bye.
Thank you.